Hey everybody, welcome back to chemistry. And so in this presentation, I want to talk about when equilibrium occurs in chemical reactions and what do you see when a chemical reaction is at equilibrium. So if we can increase the slide. So what I have here is a summary slide that talks about when you can have an equilibrium. And so my goal is pretty much to go through all these points on this slide right now. So if I can decrease the slide. So there are basically two kinds of chemical reactions that can occur. One kind of chemical reaction that can occur is an irreversible chemical reaction. And when you have an irreversible reaction occur, that reaction can never go to equilibrium. On the other hand, another kind of chemical reaction would be a reversible reaction. And at certain times, a reversible reaction will go to equilibrium. So first, let me talk a little bit about what irreversible chemical reactions are. So irreversible reactions are ones where you have all reactant molecules converted to products. And then once that happens, the reaction stops. And the reason why the reaction stops is because none of the products want to combine to reform reactants. So let me give you several examples of this. So one example we saw in a video in one of the last presentations was when Niall Red took sodium metal and added it to water, and he produced sodium hydroxide and hydrogen gas. And so that was an irreversible reaction. So let me write this on the screen really quick. So we had sodium metal, so it was sodium, and the state of the sodium was in the solid form, and he added it to liquid water. And then those were the reactants. And then they went ahead and reacted and produced sodium hydroxide, which is a compound that was found as ions in aqueous solution, and it generated some hydrogen gas. All right. So again, in this reaction you saw is that he threw these reactants together, and then pretty quickly these reactants disappeared and formed these products. And then when all the reactants disappeared and they were all converted to products, the reaction stopped. So that would be considered an irreversible reaction. So after the reaction stopped, this did not happen. You did not have these products here, sodium hydroxide and hydrogen, binding together to reform reactants. That did not happen. And so with this particular reaction, that would be difficult to do. And the reason is Niall Red carried out this reaction just, say, on open table in atmospheric conditions. And so as this reaction was going, the hydrogen gas that was generated was released into the atmosphere. And so it would be extremely difficult to somehow hope that there might be some hydrogen molecules that would recombine with the sodium hydroxide in the solution to form these reactants. So this is an irreversible reaction. And again, importantly, cannot achieve equilibrium. So Niall Red also did another reaction very similar to this, where he threw in potassium metal into water, and it produced as products potassium hydroxide and hydrogen gas. And that also would be an irreversible reaction for the reasons that I kind of mentioned, which we're applying to this first reaction here when he threw sodium into water. Okay, so this reaction was fast, as we talked about before. Now, you might ask, well, how about that slow reaction? Is the slow reaction also irreversible? And the answer is yes. So if you take carbon in the form of diamond, which will be in the solid state, and it reacts with oxygen in the air, the oxygen is in the gaseous state, it will produce carbon dioxide also in the gaseous state. And so here, the reactants, when they combine, will form the product. And it's pretty unlikely that the product will somehow by itself split apart and reform the reactants. And so this is also an irreversible reaction. So one thing you can see is if you have an irreversible reaction, it could be a fast reaction or it could be a slow reaction. Okay, so let's compare an irreversible reaction to a reversible reaction. So here I'm going to write reversible, and to note this can achieve equilibrium. A great example of the reversible reaction is the one that's kind of mentioned in your textbook. And so here you might say have in a closed container some carbon monoxide gas, and also maybe in that container you have another reactant, which would be water vapor. It would be water in the gaseous state. So it could be that the conditions here are fairly hot to keep the water in the gaseous state. So I'm going to write water, but here again it's vapor, it's in the gaseous state, so I'm writing a G there. And so what they can do is they can react and combine and then rearrange the atoms and split off to form products, and those products will be carbon dioxide, which will be in the form of a gas, and also hydrogen, which is also in the form of the gas. Okay, so this reaction is reversible. So let me explain why. So maybe you have some kind of closed container, and maybe you inject the carbon monoxide and water into that container, and maybe it's under some pressure and it's under some heat, and so these molecules will react immediately. Now, when they react, what will happen is they will disappear and then products will appear. So what will happen over time is that these reactants, the carbon monoxide and water, will slowly decrease in concentration, yet the products here, what will happen is they'll build up. They'll slowly increase in concentration, but due to the nature of these molecules, what might happen after a certain amount of time is that the carbon dioxide will combine with the hydrogen gas and reform the reactants. And then eventually what will happen is that the carbon monoxide and water will be going forward at a certain rate of reaction. And then the carbon dioxide and hydrogen at that point in time, maybe they're doing the reverse reaction to form reactants at the same rate. So when that happens, you have equilibrium. So when you have equilibrium here, if we have it, then what we do is we indicate that by showing that there is a reverse reaction, and to indicate maybe that the reverse reaction can go at the same rate as the forward reaction, we have this reverse arrow of the same length as the forward arrow. So when we have two arrows, one pointing to the right and another pointing to the left, that is between the reactants and the products, that indicates to us that this is a reversible reaction and could achieve equilibrium. Okay, so one of the things you're going to have to be able to do, maybe on a test, is here, if we have this reversible reaction, is to understand what the forward reaction is and what the reverse reaction is. And so the forward reaction is where you take these reactants and they become products. And so we would write it like this. So I probably should say forward reaction. And so it's going to be carbon dioxide, I'm going to leave out state symbols, plus water goes to carbon dioxide plus hydrogen gas. And so you can see that upper arrow here in these two arrows, this represents the forward reaction. So what would be the reverse reaction? It's where here you're seeing them as products now, but they will react and form the original reactants. But because these are reacting, we now write them first in the reverse reaction. So these are the reactants in the reverse reaction. So here, with the reverse reaction, we write carbon dioxide plus hydrogen gas gives you carbon monoxide plus water. So as I kind of point out with reversible reactions, when you start the reaction, it will not be at equilibrium. But if you wait enough time, the reaction will go to equilibrium. So what I want to do is talk about some of the properties that you will see about a chemical reaction at equilibrium. So I'm going to erase all this, and I'll be with you in just a second. Hey everybody, welcome back. And so what I want to do is I want to describe equilibrium to you by using a model or analogy which I call 3 stores on Black Friday. So if I can increase the slide. So here I have a description of this model or analogy, and what I'm going to do is I'm going to go through all these points on the board. So if I can decrease the slide. Okay, so what I want to do is I want to investigate how 3 different chemical reactions can go to equilibrium. So we have the first reaction here. The reactant is molecule A, and then the product is molecule B. And so there's going to be a forward reaction where A goes to B, and there's going to be a reverse reaction where B goes to A. There's a second reaction. Here the reactant is C, and the product is D, but this is also a reversible reaction. And we know this is because we see a forward arrow and a reversed arrow. And same thing, this third reaction here, it has a reactant that is E going to the product F. It's reversible reaction. And so to model this, we imagine perhaps that what we're looking at is the morning of Black Friday. And so if you don't know what Black Friday is, it's the day after Thanksgiving. And that is a time where shoppers think they can get great deals in department stores. And so you have a lot of people getting up early in the morning to get to these stores so they can get the best deal they possibly can get. So what we're imagining here is we have 3 different stores. And so here what I'm going to do is represent here people as dots. And so right now imagine that we have 100 people outside of this store, 100 people outside of this store, and 100 people outside of this store. And so here, what we'll say is that the people outside of this store are molecules, that these are the reactant molecules, and that anyone who gets into the store is going to be considered a product molecule, which is B. And so also we have another store. Outside the store, there are 100 people, and so we can think of these as the reactant molecule C. Anyone within the store is the product molecule D. And here in this store is, we have these people out here, the 100 of them are the reactant molecules E, and inside the store they would become product molecules, or F. So all 100 people outside the store have similar personalities. All of them want to buy toys. However, these 3 stores are different. And so this first store is a store called Toys R Us. So this was a big toy store back in the day. I don't know if it still exists. It may still exist. Hopefully it still exists. And so here we have another store, which you probably heard of. It's called Macy's. And then finally we have a third store, which is called Sears. Okay. So let's look at this first analogy here of this first reaction of between A and B. And so here we have all these people here outside the stores. They all desperately want cheap toys. And so here, all these 100 people outside the store, they are outside the Toys R Us store. Now, let's say it's 5:30 in the morning. And so that may imitate the situation where you're starting out with all reactant. And so that would be the beginning of the reaction. So imagine what happens when you open the doors at 6 o'clock. So we have 2 doors that open. We have the upper door and the lower door. And so here what will happen is people will go into the store. And so imagine this is the forward reaction where some of the people outside the store really want to go into the store. And so you have people flowing into this Toys R Us store at a certain rate. And so it might be quite fast at first. Say it may be 20 people going into the store in an hour. And so if that's the case, then people start disappearing from outside the store and the store starts filling up with people. Now, what will happen is as the number of people outside the store disappears, then there's not as many people out there to flow into the store. So although the rate of the forward reaction was initially, say, 20 per hour, it will decrease over time. So it might decrease to, say, after an hour to 15 per hour, then 12 per hour, and so on. And so you have more and more people building up in the store. And so what that indicates here is that when this reaction gets going, some of A is converted to B. Now, what happens at a certain point of time, you'll have enough people in the store that some of them will have purchased their toys and they're going to want to start to leave. And so they'll go out through this door here. So this would imitate the reverse reaction. And so what will happen is when you have a few people in the store, the reverse reaction is pretty slow. But as people start building up in the store here, what will happen is the reverse reaction will go faster and faster. And so say the reverse reaction may start out at, say, 2 per hour. But as it builds up, it just goes faster and faster and faster until you may get to the point here where the forward reaction has declined to, say, 8 per hour, and the reverse reaction has gone up to 8 per hour. And so when the forward reaction is exactly the same as the reverse reaction, then you are said to have achieved equilibrium. So let's look at some of the properties of this equilibrium. One of the properties of this equilibrium is that you can see in this particular equilibrium, we seem to have more people inside the store than outside the store. And that could be true for a particular reaction. It may be that when you start this reaction, it won't be at equilibrium, but when you're at equilibrium, it could be that you end up having more molecules of B than A. At equilibrium, the number of B molecules, even though you have more of them than A, the number of B molecules will be constant over time. Same thing with A. You have fewer molecules, but they will be constant over time. Another important property of equilibrium is you can see even when we get to equilibrium, the forward rate is the same as the reverse rate. Molecules are still moving around. They're still shuffling between A and B. And they continue to shuffle between A and B at the same rate of the forward reaction as reverse reaction through time, as long as you still have the equilibrium. So to describe that these molecules are shuffling through this equilibrium, we say that the equilibrium is dynamic. Okay, so one thing we might want to do to characterize this equilibrium is we might want to evaluate the number of product molecules compared to the number of reactant molecules. And so we can do that pretty easily. We calculate a constant called K. And so K, we'll say, is going to be equal to the product molecules divided by the reactant molecules. Now, one of the things I want you to notice, is that we have brackets here in front of these words. What the brackets mean is that we're really not exactly referring to the number of molecules in and of itself. Really, we're looking at the concentration of molecules. And we'll talk more about that later. But for now, we'll just say the concentration of the molecules right now for this analogy is the same as the number of molecules. Okay, so here you can calculate a value of K by, at equilibrium, taking the molecules of B and dividing it by the molecules of A. And so let's say at equilibrium you have 80 molecules of B and you divide it by 20 molecules of A. And so what you find is the value of K is 4. And so here we're going to make a very important point. If you have a chemical reaction that goes to equilibrium and you calculate a value of K and you find the value of K is greater than 1, that tells you at equilibrium you have more products than reactants. Okay, so now let's go ahead and look at an imitation of this second reaction where C is in a reversible equilibrium with D. And so we'll start the reaction again by having all C molecules here. And all C molecules, we can say that we can imagine these are 100 people outside the store. So needless to say, before we start this reaction, we are not at equilibrium. Okay, so we're going to open up the doors to the store. And so here it may be a little bit different. So here, these people want toys as much as the people in this other model here, A and B, but the problem is this: Macy's does not have as many toys, and so the customers out here are not quite as excited to get into this store as they were the other store. So here with Toys R Us, when they opened the door, started the reaction, and you had 20 people going to the store per hour. Here, it's going to be maybe a lot less. Maybe it's only going to be 10 people going in the store per hour. So again, the people go into the store, and this represents the forward reaction. And so what happens is as people go into the store, the number of people start building up. And so maybe what will happen is, although you start at 10 per hour, because there are few people outside the store, this rate will slow down. And then eventually what will happen is, as you might expect, you have the reverse reaction begin. You have enough people in here such that the reverse reaction again begins. And so here people leave the store. And so what might happen is that you start out with a slow rate of people leaving the store, but it builds up. So maybe here the forward reaction starts at 10 per hour, but maybe it drops slowly to 5 per hour. Here the reverse reaction starts, but maybe it slowly builds up to 5 per hour. And at that point where the forward reaction is 5 per hour and the reverse reaction matches it at 5 per hour, you have then achieved equilibrium. Now, what we can do is we can, again, analyze this particular equilibrium of this particular reaction in the same way. What we can do is we can take the number of products and divide by the number of reactants. In this case, it would be the concentration of D divided by the concentration of C. So it could be with this reaction that maybe at equilibrium you have as many C molecules as D molecules, meaning you have as many products as you have reactants. And so if that's the case, in this model it would be 50 inside the store, those are the D, and 50 outside the store, which is the C. So here what we have is 50 divided by 50. And so you do that calculation, and the value of K here for this reaction is 1. So if you have a chemical reaction where the value of K is equal to 1, that tells you that at equilibrium you have as many of the product as you have the reactant. Okay, so let's look at the last story here. And so here we're going to model the reaction E going to F. This is a reversible reaction. So the analogy we're going to use here is that we have these customers, the E molecules, outside the store. They really want toys, but the problem is this. Inside the store, it's Sears, and they don't have any toys. And so what might happen in this particular reaction is, yes, as soon as you open the doors, you do have a forward reaction here of E going to F, but it's not very fast. It may start off not at 20 per hour or 10 per hour, maybe it starts out at 5 per hour. So very slowly the number of people in the store build up, and so that means is that very slowly here E is being converted to F. And so a little bit of E disappears and goes into the store and becomes F. And so at a certain point, as you might expect, there will be enough people in here that some of these people inside will leave. And so here we start out at a very slow rate, but as you might expect, as the number of people build up in the store, we're going to finish off at some rate which matches, and as you might expect, you're going to finish off when the reverse rate is going to be the same as the forward rate. And these rates could be very low. So maybe they're like 2 people going in the store per hour and then 2 people leaving the store per hour. When those rates are the same, again, you have achieved equilibrium. But I want you to notice here, it's a little bit different this time. So here we have very few of these people wanting to go in the store. And so at equilibrium, most of the people are still outside the store, which implies that you can have this reaction reach equilibrium, but maybe that only some E molecules will become F. And then there are a few F there, but they return, a lot of them return back to E. So at equilibrium, it could be that we still have a lot of reactants and not so much products. And so here, maybe in this example, we have not so many products. Maybe we have, say, 10. And then for reactants, we still have a lot. We have 90. So what is that? Well, I think if you take 10 and divide by 90, I think what you get is 0.111. And so this makes the point that if you have a value of K below 1, what that implies is that when the reaction has achieved equilibrium, you still have a lot more reactants than products. Okay, so in the next presentation, we're going to actually look at chemical reactions and do similar calculations to find values of K. So thank you for listening. We'll see you next time.